In this video, I'll show you everything you really need to know about calculating impedance. So what's the point of impedance? Well, the point of impedance is so that you can add the quote-unquote impedances of all the capacitors, inductors, and resistors, right? You can't add ohms with henries with farads. Okay, that's just completely impossible. And if you wanted to do math with these stuffs related to voltages and currents, if you want to solve for the voltage and currents at these locations, then you would have to use differential equations. But you can actually use the complex plane and impedances to calculate voltages and currents, right? Let's show you how to calculate impedance. So how do you calculate impedance for this guy? Now, first off, I just want to say impedance is represented by a Z. Okay, so Z is simply equal to your resistance. For a resistor, the impedance is the same as the resistance. All right, what about for an inductor? Well, your impedance at an inductor, Z, is equal to the imaginary number J times your angular frequency of your current or voltage times the inductance. So just simply whatever you have in henries is your inductance. And for your capacitance, for your impedance for your capacitor, it's simply J angular frequency and capacitance. But here's the thing about this: technically your impedance is negative, right? So if you multiply this by J over J, you actually get J squared, right, in the denominator. So you get J over J squared angular frequency capacitance, but J squared is simply -1, so you get negative J over angular frequency C. So you're mostly going to be using this formula right here to calculate the impedance of your capacitor. And the thing about all these impedances is that you can treat them just as ohms. The unit for your impedance you could just simply treat as ohms. And what can you do with ohms? Well, with ohms, you can have resistors in parallel. So let's go ahead and actually look at this circuit right here, or resistors in series too. Let's go look at this circuit here, some other circuits to the left and right. We can actually combine all of these into one singular resistor, quote unquote. Now the reason why I'm saying quote unquote is because this technically isn't a resistor. I'll just represent it with a box, yeah, right? And this box has some unit of resistance. And here's the thing about this. I'll explain this later, but you can actually use Ohm's law with this guy to solve for current. So let's say this is Z, okay? This is your impedance box. Let's use a different color, Z. Let's move this up for more space. Oh no, cuts off. So this right here is your circuit, and let's go ahead and calculate the impedances for all of these guys right here. So what's the impedance for your resistor? It's just 5 ohms, right? The impedance is equal to just your resistance. All right, how about your inductor? You have 3 henries times the angular frequency times the imaginary number. In this problem, we can pick some random angular frequency, 100 radians per second, okay? So you have J times 100, right? That's your angular frequency, times your inductance, which is 3 henries. So 3 times 100 times J. This is simply 300 J ohms. All right, what about your capacitance? You have 5 millifarads. So this is 0.005 farads, correct? So you have negative J over 100 times 0.005 millifarads. Well, if you simplify this, you simply get J over 0.5, which is equal to, negative 2J over 0.5, which is equal to negative J2. Okay. So this right here, oh, I gotta move this down, has an impedance of negative J2. This right here is an impedance of J300, and this right here is an impedance of 5. Well, since these are technically all in series, we can actually just add every single impedance together to get a singular impedance box. So These are in series. Our unit for impedance is in ohms, so we can add all these together. So what do we get? We get 5 plus J300 minus J2. And what this turns out to be is 5 with the real part of your complex number plus J298 ohms. Right, that we just simply added all these numbers together, and we actually just get a complex number right here. And this complex number is actually the impedance of your impedance box, okay? After combining all together. And what you can do is you can use Ohm's law still. So R is equal to, voltage, V bar. So I'm going to put a bar on top to clarify that this is a complex or a phasor or a polar coordinate in the phasor domain. Okay, times I is equal to I R. Actually, IZ, your impedance. What we have here is just simply Ohm's law, right? Voltage is equal to current times resistance, and Z is in the unit of ohms. Well, since I have your impedance here, right? That's a complex number. What you want to do is actually turn it into a polar coordinate in the phasor domain so that you can multiply your polar coordinates easier. But that's besides the point, okay? All this video should be about, before I went off the rails a little bit, is how to calculate impedance, all right? And these impedances still follow rules of KVL, KCL, right? But you just have to learn how to use imaginary numbers, all right? Imaginary numbers aren't too bad. You'll get used to them. But if you don't know how to turn this into a polar coordinate or turn this into the phasor domain, I have videos on that too. Links will be down in the description for everything related to all the complex numbers related to electrical engineering, right? It's for circuit analysis. But what I showed you were, these elements in parallel. If these elements, these elements in series. If these elements were in parallel, you would add their impedances like so, with the same way you would add the resistors in parallel. So you have Z over Z1 plus 1 over Z2 plus ... 1 over Zn, however many things you have in parallel. But I really don't have much more to show about impedance. All you got to do is follow these formulas, right? And you'll get some ohm value. And you can add up all these ohms the same way you would add up resistors. So you can actually treat inductors and capacitors as resistors if you wanted to, and you can actually use Ohm's law for them. Maybe a helpful example of this would be, let's erase a little bit. Helpful example of this would be, let's say some voltage source was here, right? You had some resistor, some inductor, and some capacitor. All these were in series, and you combined it into something with impedance. Okay, so let's call this Z. Well, if this voltage source had, let's say, 50 cosine of 30t plus 20 volts, okay, you could actually use KVL on this, right? So this would be 50. This would be 50 cosine of 30t plus 20 volts. You can actually just simply use KVL on this, and you would still be able to find the voltage at this impedance element. I actually don't know the formal name for that. Maybe I should have looked at that. But you guys get what I'm saying, okay? So you can still use KVL for this, and when you use KVL, and if you have the impedance at this as well, that means you have the voltage at this impedance, impedance location, right? And since you have the voltage at this, you can just simply use Ohm's law. You can divide your impedance, but your voltage in the complex form over your impedance, right, to get your current. Now keep in mind these need to be AC circuits for this to work. But that's really all it is to this video. Impedance, not too complicated of a topic. If you need any extra help, of course, I have videos with practice problems on those. I will leave those down in the link in the description for your convenience. But as always, if you have any questions, put it in the comment section. If you found this video helpful, consider subscribing, like the video. Thanks, bye.